I need. So we're going to look at this idea of numerical integration for definite integrals, but we'll start with what you already know, and that is finding the answer to definite integrals by adding areas of rectangles. So you may have forgotten that you actually did this, and that's okay, but I'll remind you. Okay, so recall in Calc 1, this is right when you were starting the whole module on integration, okay? This is what they did. They gave you some graph of some function, y equals f of x, who knows? And they said, hey kids, I want us to find the area under the graph. Okay, and I'm just going to show you it in here. Go get that area. And they're like, oh boy. Now you know how to find the area. Of course, you use a definite integral, but when you started, you didn't know how. And so this strange shape is not something that we have an area formula for. I don't know how to find the area of something that's got this curvy top to it. So what we do in Calc 1 is we reduce this to a problem of areas that we do know how to calculate. So it's the divide and conquer technique. Everybody knows how to find the area of a rectangle, and so we use the knowledge of area of a rectangle. You know, area of a rectangle is length times width, right? Y'all can buy that. And so what the Calculus 1 instructor did is they looked at this interval going from A to B, and they first chopped it up into equal subintervals. So, you know, I'll just do a little bit of this. And, you know, how many depends on the problem. Okay, you can have a lot or a little. But either way, once you chop it up into equal subintervals, then you start creating rectangles. Okay, so the first rectangle, and this is where you have to decide if you want to do leftmost endpoint or rightmost endpoint. How about if I go leftmost endpoint? And so the actual height of our rectangle is this height here, which is f evaluated at A, yeah? So this area of this rectangle is the width down here times the length, which is here. And so the area of one little triangle, I'll call it A sub I, was the width. And by the way, all of those little widths can be found by taking the length of the entire interval, b minus a, and dividing by the number of subintervals. So I think I cut this up into 8, didn't I? Something like that. So my n would be 8 here. And so the width, this is equal to your width. So b minus a over n, that's your width, times your length, and that's just the function evaluated at that endpoint. And so what you do is you keep going. You go, well, I know how to find areas of rectangles. Cool. So then I'll find the area of the next rectangle right there. So, you know, we'll add to that, you know, the next rectangle. And his width is still b minus a over n, whatever your n is, and mine was 8, times his length. But his length is f evaluated at, and we'll call this first point x1, and so on and so on. And so what you end up doing is you start adding up all of the areas of the rectangles, like so, and it gives you a pretty good approximation of the total area. So the approximate area, and you did this in Calc 1, people, is the sum, and they use a sigma to represent sum. And we're going to be doing a lot of sigmas, and we're going to start next week. And sigma is the Greek letter S, which stands for sum. And you're going to have I starting at 1 and going to n, because I have n rectangles there. In my case, I have 8 rectangles. And you're going to basically take the area of a generic rectangle, width, times the length, which is f evaluated at, say, x sub I, and then there you go. And this is known as a Riemann sum. And eventually what you did to get the actual area is you took a limit as the number of rectangles increased, because if you start increasing the number of rectangles in here, in other words, tightening up your partition down there, you end up with better and better approximations of your area. So the actual area ended up being the limit as n approaches infinity, but it's better if you take the norm of the partition going to 0. That's just basically chopping up your interval into tighter and tighter subintervals. And when you take the limit of this Riemann sum as you tighten up your partition, it turned into the integral going from a to b of your function. And then this right here ends up being your delta x sub I here, your width, and the delta x sub I turns into your dx essentially. So a quick poll of the class. Does anybody remember seeing this kind of process in a Calc 1 class?
Yes.
Yes.
Oh, thank goodness. Okay. You're just going to see it again today. But we're going to do a little bit better approximation. Instead of rectangles, we're going to use trapezoids. And then the second shot at it is we're going to use sort of rectangles with curvy tops that'll even be better than the trapezoid method. Okay, so that's our plan. So I'm hoping that you saw this idea in Calc 1 because we're just going to revisit this idea of finding the area under a curve using numerical integration techniques. But instead of rectangles, we'll do a different shape. Okay, so that's the plan. So here we go, the trapezoid rule. So instead of drawing rectangles underneath your curve, you're going to connect the two endpoints here. And so this, instead of being flat on top like we did when we had the rectangle method, these tops are going to be line segments here. And I hope you can appreciate that if we did the rectangle method like we were doing with the leftmost endpoint, if we added up the areas of the rectangles like you did in Calc 1, do you see that you've got a lot of space that you're not accounting for your area? So that would be a pretty poor approximation of the area because you got all these gaps. So a better approximation instead of adding up rectangles is add up trapezoids. Okay. All righty. So then what? You still are going to start off the same way. You're going to subdivide the interval. I'm going to, every time I use my erase feature, I end up erasing actual, yeah. So there we go. So you're still going to start down here with what I call a grid. You're going to want to start with your leftmost endpoint up to your rightmost endpoint and chop it up into equal subintervals. This is important that you do that correctly because you need to know what these intermediate values are because you're going to have to evaluate your function at those values. So it's important that you chop it up nice and your grid looks pretty. So then you are able to say that each delta x, so delta x is one width here, delta x is equal to width, just like we had for the rectangles. And it's just like you did in your Calc 1 class. It's the length of the entire interval divided by the number of subintervals you're asked to use. And they're going to always tell you this. They will tell you in the problem. Usually it's a nice number that's not too bad, like 3 or 4. We're going to do some 3s and 4s, but we're also going to do 8s, which is a little bit of a hassle. Now, when I was giving you the homework and picking out homework problems, I tried to avoid the homeworks where they asked you for a huge amount of subintervals, like 16 or 32, because it's like, oh my goodness, I don't even want to do that homework problem and have to sit there with a calculator and figure out the function 32 times. So I certainly don't assign the kinds of homeworks that even I wouldn't want to do. Okay, that's mean. All right, so then you will look at one trapezoid there. That's a trapezoid, it's not a rectangle. If I flip the trapezoid over on its side so you can kind of look at it better, there it is. I'm going to do some 5th grade math here. Well, maybe you should have learned this in 5th grade. I don't know. I don't know what they're learning in 5th grade these days. But how do you get the area of one trapezoid? And I want to go over this in case you forgot, because you may not know. So I'm not trying to be weird or anything, but you have to know some of the quantities. So you have to know the length of the side that's touching the ground. That's called base 1. And then the length that's parallel to that is base 2. So you have to know the lengths of base 1 and base 2. And then how tall your trapezoid is. And this height right here, h, is how tall it is. I don't care about this leg over here. That's just not helpful. And so the area of one trapezoid is you take the sum of the two bases, base 1 and base 2, you divide by 2, and you multiply the whole thing by the h. Has anybody seen this trapezoid formula before?
Yes.
Okay.
Yes.
Now, for us, because, you know, we really flipped it back over on its side, so this down here is this length down here. So for us, that's not really a height anymore. It's kind of like this width down here. So for us, the area of one trapezoid, we're going to change it up a little bit. We're still going to divide by 2. This h is going to be that width down there, which is the quantity b minus a over n. And again, they're going to give you the n. Don't worry. They'll always give it to you in the problem. Now, what is the b1 plus the b2 for us? Well, for us, this base here is just the function evaluated at that leftmost endpoint. That's how tall that leg is. So f evaluated at that leftmost endpoint plus, and then the length of this other base here is just f evaluated at the other endpoint, x1. And boom, there is the area of your very first trapezoid. Pretty cool, huh? Looks kind of messy, but it works. Now, you're going to actually have, you know, a whole bunch of trapezoids here. Oops, I'm not drawing very equal subintervals. And so you want to figure out what is the area of a generic, you know, just pick one weird trapezoid here and what's his generic area. So you're still going to have that width. That's not going to change because the subintervals are equal. But his bases, his B1 and B2 may be different. So one will be like the left endpoint, so you're evaluating your function at the left endpoint, and then you evaluate your function at the right endpoint of that tiny little subinterval, and then divide by 2. Okay. Now, what happens is you end up with the area. Here's the area of the first guy that we already did. Now, I want to do the area of the guy that's right next to him, even though this is a hot mess here, because I want to make a point about something that may not be obvious. So if I create the second trapezoid right here, here he is, what is his area? It's still going to be B1 plus B2 over 2 times his width, which is the same as the first guy, B minus A over N. But I want you to notice this length right here is F evaluated at X1 plus this length here, we'll call this X point X2. You know, and you'll keep going, X3, X4. So what I want you to notice here is this is the second trapezoid. And over here was the first trapezoid. Do you notice the first trapezoid's rightmost endpoint, the f of x1 leg, is repeated here? You have to use it again, essentially, when you're finding the area of the next trapezoid. Please say yes.
Yes. Yes.
Yes.
Okay, and that is why after you've added up, this dot, dot, dot means, you know, there's all the other trapezoids in between the first one and the last one. This is the very last one, and this is the very first one. The middle guys have repeats. So if you factor out this common factor of a half, so there's where the 2 went, and then you look at the sum of all the numerators, fx0, which is the furthest leftmost endpoint, never gets repeated because he doesn't have a trapezoid right next door to him. But all of the other legs of all the trapezoids get doubled because they get used up twice. But the very last endpoint does not get repeated. So if you add like terms of all the ones that get used up twice, because those trapezoids are butted up right next to each other, you'll see these 2's show up in all of the other valuations for the function, okay? So that's the whole idea. I'm going to skip the rest of this derivation. It basically proves to you, if you want, you can go look at it. For you math majors, you should understand it. But it ends up where you take the limit of the Riemann sum and it does give you back the area. So it basically is a very good approximation of the, as long as you subdivide that subinterval and into your, tighten up your partition. So what does the trapezoid rule actually say? So from here, I go directly down to the theorem. And it says if you're going to use the trapezoid rule, first you got to make sure you have a nice continuous function, otherwise forget about it. And then instead of actually evaluating the definite integral, you set this up. Now, if you're a thinking student right now, and I hope that's everybody in the class, you're going to probably be thinking, why do I even want to do this? This seems horrible. Why don't I just find the area using the integral? I mean, because this looks like a pain in the rear end. And I would agree with you. Like, you're absolutely right. Like, who would want to do this? This sucks. This is easier. But here's the deal. When you are given an integral that's not integrable by any of the techniques that we've used before, even if you had a table of integrals, might not even be in there, it's just not doable, you can still find the answer, the area under the curve, if you use this numerical integration technique. And that's the beauty. So I do want you to appreciate the beauty, okay? So you're going to have your b minus a over 2n, and then I promise you, they'll give you the n. And then you'll have the function evaluated at the furthest left endpoint, and then all of the middle points of your subintervals, you evaluate and multiply by 2, except for the last guy, because that very last endpoint doesn't get duplicated. And that's it. So we're going to do the trapezoid rule on a super easy problem where I agree it's overkill. We don't even need the trapezoid rule to get the answer. Come on, let's get real. But it's just a way to start off easy so you can see the process. So let's do it without the, this is just for kicks and giggles. Let's see what the actual answer is. I hope that you would agree this is a calculus 1 problem. Everybody knows how to integrate sine x. It's negative cos. And you would just evaluate from the limits 0 to pi. So I put my bracket over here. That's a bracket. Good notation, people. And then you go, okay, I'll evaluate at the upper limit, which is pi, minus, and then I'll evaluate at the lower limit, which is 0. What is cosine of pi? Does anybody in the room remember?
-1.
Good. So you're going to go negative, -1, and then this minus is a plus. And then does anybody remember what cosine of 0 is?
1.
So then this looks like 1 plus 1, but that's above my pay grade, and the answer is 2. And that's the actual answer. So we don't even need the trapezoid rule. We're going to use it. And let's see how this works. This is numerical integration. Now, how many computer science majors are in the room? Give me a shout out.
Yeah.
Yay.
Me.
Okay, go in the chat box. 1, 2, 3, 4, 5. Go in the chat box and say something. I got 5. Is that it? 6, 7, 8, 9, 10. Ooh, God, 11, 12, 13. Wow, we're getting to almost half the class. All right. Oh, there's more. Holy crap. Look at all these computer science majors. All right. Cool. All right, computer science majors, talking to you. This whole section is like right in your wheelhouse. And if you already took Math 130, or I'm hoping you did, and so I know some of you are in my Math 130 class right now, so we could, I claim using loops and this idea of you know how to find the area of a trapezoid, you could use a loop, and if somebody gave you the n, you could use it and use this trapezoid formula to find the area under a curve of some given function. So that would be a cool, cute little loop problem, not hard at all. And for those of you who've already discussed methods, you could write a method where you would give it 2 parameters, or actually you probably need to give it 4 parameters. You need to give it the function that you're trying to find the area of. You need to give it the n, the number of subintervals, a leftmost endpoint and a rightmost endpoint. And when the method would have those 4 parameters, you'd have a little loop inside your method. It would chug along and get the area, pop out the area, baby. Wouldn't that be cool? Who's excited? That's giving me ideas for a lab for next semester. Ha, ha, ha. Okay, if you haven't taken Math 130 yet, this is my time to do a shameless plug. Yep, I'm going to do a shameless plug. So for those of you who are math or computer science majors rather, and even if you're an engineer major, you should be taking a programming class, because you know what? Everything is in code these days. Everything has a computer in it. I mean, even your has a microprocessor in it these days. Let's be honest. And Math 130 is Intro to Computer Programming using Java. And the only prerequisite is intermediate algebra, and everybody in this room is a graduate of intermediate algebra, so you're all welcome to come. And I'll be teaching 2 sections next semester. I'll be teaching Tuesday, Thursday at 8:30 in the morning, and Mondays and Wednesdays at 11:45. So I'll see you there. Okay, back to the matter at hand. We're going to do this problem, which we already know the answer to. The area is 2. But we're going to do it when n is equal to 4 and when n is equal to 8, just to see, you know, what the different answers are. You know, and if you're doing computer science and you had your method there, wouldn't it be interesting to feed it different parameters with different n's? So first up, you got to look at your grid here. Notice if they're telling you that the original interval is 0 to pi, so you have 0 to pi here, and then they're telling you n is 4, you have to chop up 0 to pi into 4 equal subintervals. So the way I usually do it, so I don't screw up, is first I cut it in half, and then I cut it in half again, and that way I can, well, that doesn't look very equal, but it's good enough. So then I know halfway in between, well, halfway in between 0 and pi is pi halves. And then this point right here is where x is pi fourths, and right here is where x is 3 pi fourths. So you have to make sure you've got your grid set up pretty. So then, now you just know your n is 4, your delta x, which is b minus a over n, in this problem is pi minus 0 over 4, which is pi fourths. So your area, and this is the approximate area, of course, is b minus a over 2n. Times the quantity fx0, that's the leftmost endpoint, plus, and we have 3 intermediate points. So you're going to go 2 fx1, and we know what fx1 is, pi 4. So I'm just doing sort of the generic look here. Plus 2 fx2 plus 2 fx3. And then the last guy is not duplicated. That's just, there's no 2 multiplied with that last guy. So for us, when we plug in the values that we have, we're going to have f evaluated at the leftmost endpoint, 0, plus 2 times f evaluated at pi fourths, plus 2 times f evaluated at pi halves, plus 2 times f evaluated at 3 pi fourths, plus f evaluated at the rightmost endpoint, and it's not multiplied by 2, f evaluated at pi. But what is the function we're evaluating? Well, f of x is sine of x. It's the integrand of your integral. So this right here, after simplifying, is pi eighths. This is going to be sine of 0 plus 2 times sine of pi fourths plus 2 times sine of pi halves plus 2 times sine of 3 pi fourths plus 2, not 2, whoops, I almost said it wrong, plus, not times 2, just regular sine of pi. And then you have to figure out all those, right? And so hopefully you remember what your sine values are. Sine of 0 is 0, and sine of pi fourths, I believe, is square root of 2 over 2. Sine of pi halves is nice, it's 1. Sine of 3 pi fourths is also square root of 2 over 2, and sine of pi is 0. And you add all this mess up. Now, sometimes my math lab might want a decimal answer, and sometimes it might want the exact answer. So some of you, I noticed, you're still getting familiar with my math lab. When you accidentally don't follow directions, it gives you 0 points. Now, I come in there, I swing in, and I give partial credit, but please follow directions. If they wanted the exact answer, you would have pi eighths. And then these guys are like terms, so 2 apples plus 2 apples, and when I add them together is 4 apples. And then this guy is not like, this guy reduces to lowest terms, And so the exact answer would be, say, pi eighths times 2 square root of 2 plus 2. That's good enough for me, okay? If you wanted to clean it up a little bit, you certainly could factor out a 2 from the sum, and then you could reduce this to lowest terms. If you wanted to make it look as pretty as possible, there's your exact answer. Now, your approximate answer is, that's when you whip out the calculator, and this is approximately 1.896. Now let's compare that to the real answer. Is this a good approximation, yes or no?
Probably so.
Okay, what makes you say probably so?
Because it's closer to 2.
Pretty close to 2. Not bad. I'd say it's pretty darn good. I'm impressed. Now, if you're not impressed, then you're not doing it right. That's all I can say. So we're going to do the problem all over again, but now what if they ask for 8 subintervals? Oh man, this is going to take some time. Sorry. So you're like, really? Yeah. So I'm going to need another page. So if I'm going to use n equals 8 for this example, what do I know? Well, if you look at the grid now, the grid 0 to pi, and you try to chop this baby up into 8 equal subintervals, you got to be careful there. What are the, the possibilities? You're going to have pi eighths, and then 2 pi eighths, which is pi fourths, 3 pi eighths, 4 pi eighths, but 4 pi eighths reduces to pi halves, 5 pi eighths, 6 pi eighths, but 6 pi eighths reduces to 3 pi fourths, 7 pi eighths, and then 8 pi eighths, but that reduces to pi. Fine. Now what? So your area, according to the trapezoid rule, is going to be b minus a all over 2n times, woo! And so you're going to go, f evaluated at 0 plus 2 times f evaluated at pi eighths plus 2 times f evaluated at pi fourths plus 2 times f evaluated at 3 pi eighths plus 2 times f evaluated at pi halves plus 2 times f evaluated at 5 pi eighths. Oh shoot, I'm running out of room. Plus 2 times f evaluated at 3 pi fourths plus 2 times f evaluated at 7 pi eighths plus, there's no 2 for the last guy, just f evaluated at pi. Do you see why even just boosting n a little bit, it makes it kind of a pain? Now this one, because we don't know a nice value for pi eighths, this is where you're going to go, okay, I'm going to need to whip out a calculator. So, so you're going to go like, what's sine of 0? What's sine of pi eighths? Sine of pi eighths is going to be some yucky number. We know what sine of pi fourths is. Sine of 3 pi eighths, ugh, yucky number. Sine of pi halves, not bad. Sine of 5 pi eighths, oh man, that's pretty gross. Sine of 3 pi fourths, not bad. Sine of 7 pi eighths, I don't know what that is. It's something really bad. That's why a calculator is needed here. And then just sine of pi. So now you need a calculator. But be sure you're in radians mode, because these are radians that you're evaluating your sine function at. So if you're in degrees mode, you're going to get the completely wrong answer, and my math lab is going to give you a big fat 0, and then you're going to get really sad. So after you use the calculator, and don't forget to multiply by pi 16, I get approximately 1.974 after I round it. And I actually get 1.974236160. I mean, you can go for, have an infinite number of decimal places. It's crazy, but I'll just chop it at the 3 decimal places. Okay, is this a better approximation than the last time we used trapezoid rule or not?
Yeah.
It's better. So what's the point? The more subintervals you have, the better the approximation of your area. And that's the point. And that happened also in your Calc 1 when you had more and more rectangles. Questions? So before I do Simpson's rule, I'm going to go way over here. Let's do something out of order. Yeah. Here. Okay. I'm going to put you guys in breakout rooms just for like 5 minutes. And just do the first part of this example 4. Just the first part. So you're given n is equal to 3. Your interval is going from 0 to 1. And the function that you're trying to find the area under is square root of 1 plus x squared. And you're going to use the trapezoid rule with n equals 3. Now, before I put you in breakout rooms, I claim that everybody in the room could do this one by hand, but it would be a little bit tough. Why? Which integration technique would you use, or would you have to use, in order to actually integrate this by hand?
Trig sub.
Good. Lisa, right on. Trig sub, because it's a square root of a sum of squares. Now, we're going to not do the trig sub, but you could do it. It would be a pain in the butt, too. But for this problem, no trig sub. You're not going to even do any calculus. There's no calculus involved in numerical integration. You just do the formula. That's all it is. It's just plugging and chugging. So let's see. We have 30 people in the room. Wonderful. I'm going to put you in pairs. And when your breakout room opens, please join the room, okay? So I'll come and visit you and see how you're doing, all right? Bye. Oh, well. So Simpsons, you're going to have to worry about this idea of n being even. So we'll do an easy one, and we already know what the answer to this. Remember, the answer is 2, the actual answer. Let's do Simpsons. We'll do it twice, one for n equals 4 and one for n equals 8. Now remember the grid. So here's your grid. You're going from 0 to pi. If you cut it up into fourths, then you're going to have pi fourths, pi halves, and 3 pi fourths be your intermediate points. Okay, then for n equals 4, you're going to go, you're going to have b minus a over 3n is going to look like, for us, pi minus 0 over 3 times 4, which is pi 12ths. So if you use your Simpsons rule, this b minus a over n for us is pi 12ths. So your area is approximately pi 12ths times, and I'll do the intermediate step, f evaluated at the leftmost endpoint plus 4 times f evaluated at pi fourths plus 2 times f evaluated at pi halves plus 4 times f evaluated at 3 pi fourths plus, and there's no 2 or 4 here, it's just evaluated at pi. So the function for us is sine of x. So for us, we're going to go, okay, pi 12ths times sine of 0 plus 4 times sine of pi fourths plus 2 times sine of pi halves plus 4 times sine of 3 pi fourths plus just sine of pi is the last term. Ugh. And then this isn't too bad because we all know from our unit trig circle and taking trig what these values are sine without using a calculator. This is 4 times square root of 2 over 2 plus 2 times 1 plus 4 times square root of 2 over 2 again. And then I think sine of pi is 0. That makes it easy. Okay, then these guys, well, you can reduce this to 2 square root of 2. 2 square root of 2 plus 2 square root of 2 is 4 square root of 2. So I'm going to add like terms. And then this 2 is just sitting there. So this is the exact answer right here, which is pretty ugly. And if you whip out a calculator, it's approximately 2.005. So it's actually a little bit higher than the actual. How come it's a little bit more? Well, those curvy tops that we had when we were using Simpsons, my little diagram over here, let me just do it, when you're doing this diagram for sine, what you're doing is when you cut up these guys, you're not doing straight tops, you're doing these little curvy tops, little mini parabolas, if you will. And so sometimes those little curves might exceed the graph itself, so you might get a little extra area. So this is a little bit too large, but not bad. I mean, 2.005. Shoot, that's a pretty good approximation if you ask me. That's good enough for government work. Questions? Okay, what about n equals 8? Oh man, you're kidding me. No, I'm not kidding you. So for n equals 8, b minus a over 3n is pi minus 0 over 3 times 8, which is pi 24ths. So your area is going to be pi 24ths, and you got to look at your grid. And we already did a grid where we cut it up into eighths. So just to remind you when we were doing this, because I don't feel like writing it all out again, the grid for eighths was this right here. See that big mess? Look at all those intermediate steps. You know, pi eighths, pi fourths, 3 pi eighths, pi halves, 5 pi eighths, 3 pi. So if you could recreate that grid, because you're going to have to evaluate sine at each of those points, those 8 stops on the block. So here, the intermediate step here, I'll do sine of 0 plus 4 times sine of pi eighths plus 2 times sine of pi fourths plus 4 times sine of 3 pi eighths. Notice they're alternating, 4, 2, 4, 2. 2 times sine of pi halves plus 4 times sine of 5 pi eighths plus 2 times sine of 3 pi fourths plus 4 times sine of 7 pi eighths plus sine of pi. And then whip out the calculator. Oh yeah, you're not going to want to try this at home, folks. And I get 2.0. I got to have a lot of decimal points because, or decimal places, because this is super accurate. The answer here, roughly, I rounded it, 2.0003. That's pretty close to the actual answer of 2. So pretty good approximation. Simpson's rule is pretty darn good. Okay, now when you find approximations, whether you use trapezoid rule or even the rectangular rule that you did in Calc 1, or here we did Simpsons, there's always error, a little bit of error. So, well, how much error? Well, if you do some error analysis, and I'm going to skip all this, don't worry about this stuff. This is just some extra stuff you can brag about at your next cocktail party. You want to know how accurate you are. So the following theorem gives you some formulas for the errors, or how much you're off by when you use either the trapezoid rule or Simpson's rule. So it turns out when you're doing the trapezoid rule, your error will be no more. So they're giving to you sort of a cap on how bad it could be. Is your interval's length cubed divided by 12n squared multiplied by the maximum that your second derivative can get to. So you may want to have to do some calculus to figure out the max of your second derivative. And you guys all know how to find maximums because you took a Calculus 1 class. And we're going to like sleazily do an example where we just kind of eyeball what the max would be just because we can. And I'll let you do this on quizzes or exams. The error, the worst case scenario error for a Simpson's rule would be the length of your interval raised to the 5th power divided by 180 n to the 4th times the maximum that your 4th derivative would get to be on your interval. And folks, on your quizzes, don't worry about this one. I didn't give you any problems on that. I think I did give you an error problem or two for trapezoid rule. So we'll do one of those here, okay? maybe even 2. Let's do for sure 1. We've got time for that. Okay. So we already did this guy. We did the trapezoid rule on this integral already. So we did it on the first example, okay? And we did it for n equals 4, and we already did it for n equals 8. Okay, fine. So this kind of problem is they're not actually asking us for the worst case scenario for the error. So if they were, just to let, so that they're not, the error, which they're not asking for, they're asking for something else. But the error would be, if let's say n equals 4, if you use the theorem, and I don't have this memorized, so I gotta go look at it, b minus a cubed all over 12n squared, 12 times 4 squared, times, and then you have to look at the max that your second derivative could get on that interval, okay? So over here, let me do some scratch work. Let's find the second derivative. Well, if f of x is equal to sine, what's the first derivative? Haha, that's easy. Cos, right?
Cos.
Yeah, and then what would your second derivative be?
Negative sine
Mm-hmm.
x.
Mm-hmm. And so when you're looking here, and this is, they do absolute value here, if we look at the absolute value of negative sine x, and so absolute value of sine of x, say, what is the max that sine of x can get if you restrict yourself to the interval 0 to pi? Just look at the graph and tell me, like, how high is the highest it gets?
1.
1, very good. Exactly. So the error that that we would get, our error would always be less than or equal to this number here, which is pi cubed all over 12 times 16 times 1, okay, whatever that number is. But they actually didn't ask us for this, but I just wanted to show you how you would do one of these error problems. So your error wouldn't be any worse than that, which is pretty good. I mean, if I have a calculator, I'll whip out my calculator here. What the heck is pi cubed over 12 times 16? Oh, I don't know. Pi cubed, woo, divided by 12 times 16. I get 1.16149. So your error, you'll be off by plus or minus, 0.16149. And that's not very good. I'd rather have a lower error than that. But, well, there's a few ways to get a lower error. One way is go use Simpson's rule instead. Another way is to increase the number of subintervals. The more you jack that up, the lower your error, because this is related to n. So what are they asking for in example 3? They're asking you to figure out the value of n. So this stays n. You're going to solve for n. If you want your error to be less than 0.01. So this is an inequality, and they're asking you how many subintervals do you need if you want your error to be pretty tiny. You see, with the n equals 4, we just found our error is a lot higher than 0.01. It's 0.16149, which is bigger than 0.01. So we know when we solve this inequality that n is probably going to be larger than 4, because 4 didn't give us very good accuracy. So how do you solve an inequality? Well, this is just an algebra problem, people. So there's a few ways to go. I'm going to show you the way I want to go. Let me append a page, so I'll show you where to go, and then we'll be done for the day. So this is example 3 continued. So what do we have so far? So we have pi cubed all over 12n squared. We want that to be less than 0.01. So I'm going to do a little trick that you're allowed to do with inequalities. 0.01 is the same as the fraction 1/100th. And it turns out if you have a fraction less than another fraction in an inequality, if you take the reciprocal of both sides, that's legal provided you do what with the inequality? Does anybody remember?
Flip the sign.
Flip it.
Flip that inequality symbol over. So the less than turns into a greater than. Then it's still true. Okay, fine. Then what? Well, we're trying to solve for n here. And so as long as you do some legal maneuvers, you're fine. Well, how about if I multiply both sides of the inequality by pi cubed? Sure, do it. And then we have 12n squared greater than 100 pi cubed. Yikes. Then what? Well, how about if I divide both sides by 12? Sure, go do it. Then I have n squared greater than 100 pi cubed over 12. You could reduce this to lowest terms if you want, you know, divide by what, 2? Well, we could do even more. How about 4? Okay, so we really have 25 pi cubed over 3. All right, big whoop. Now what? Take the square root of both sides. Normally, you know, you would do plus or minus, but I'm not going to do that because I want my n to be positive. So screw that and keep it positive. Okay, then what? You're close, Hosan. There's one little thing you have to remember, but you're on the right track. So n is greater than this number. So whip out your calculator, because who wants to know what that number is? It's pretty disgusting. And I get 16.07437834. I know, pretty weird. Now you have to choose an n, and keep in mind, n is a discrete number. You can't, you don't want to have like, oh, I want 15.2 subintervals. You want like something that's, you know, a nice whole number. So you need to round up. So your n is actually going to be 17. Has to be a number greater than 16. So the very next integer that's greater than 16 is 17. So you would need 17 subintervals. Ooh, that's a lot. Using your trapezoid rule if you wanted to get your error down to not be more than a 0.01. Okay, and that's the point. So trapezoid rule, turns out you need a lot of subintervals to get some good accuracy. Yikes. And I'm done with today's lecture. I will stay after some time a little bit to answer any questions anybody has. Also, in a half an hour, I do have office hours at noon, so you can talk to me anytime. I'm here for you. If not, I'll say goodbye and good luck on your quiz 6, part 1, Sunday. Okay, please make sure you do that.